Hi, I'm Kemil and this is Chem with Chem. Now in this session, we're going to be working the January 2023 paper 2. We're doing a full walkthrough. Now, if this is your first time to the channel, then welcome. If you're a returning viewer, then big up yourself and I hope you've been sharing the content that you find here and I hope you've been finding value. No, we're not going to compromise quality as much as we want this to take as little time as possible. Be sure to check out all the other materials that we have here. You have no excuse now to not do well. Now remember to like, share, and consider subscribing. Let us just get right into this. All right, so first question, and of course, I should not spend more than 30 minutes on this question. So let us just go right ahead. What it says. Define the term normal salt. All right, so normal salt, the salt formed, or we could say the substance formed when all the H plus ions of an acid are replaced by the ammonium or a metal ion. So by a metal ion, by the metal or ammonium ion. That should give us our full marks. And they're asking us in part 2 to identify one other type of salt that can be formed from the reaction between dilute sulfuric acid and sodium hydroxide. No, all right, so part 1 or number 1, part A of number 1. Students were required to prepare a sample of the normal salt produced when aqueous sodium hydroxide reacts with dilute sulfuric acid. So, all right, sulfuric acid is a
diprotic or a dibasic acid.
every 1 molecule of sulfuric acid, we will get 2 H plus ions, or for every 1 mole of sulfuric acid, we will get 2 moles of the H plus ions. So 1 mole of this gives us 2 moles of that. So we say it's diprotic. Now, when all of the H plus ions are replaced by a metal or ammonium ion, we get what we call a normal salt. So we'll just write that. All right. And part 2, identify one other type of salt that can be formed from the reaction between dilute sulfuric acid and aqueous sodium hydroxide. So if it's not a normal salt, then it is what we call an acid salt. Some folks will say it's an abnormal salt, but no, it's an acid salt. So there we go, 3 marks down, just like that. So we're on to part B. The normal salt was produced by conducting a titration. The normal salt was produced by conducting a titration. The students were provided with a dilute solution of 4.9 grams per dm cube of sulfuric acid. Very important, we're given the mass concentration here. We're given 5 grams of sodium hydroxide, the base, and we're given methyl orange indicator. They carried out the procedure outlined in parts A and B. The titration results for part A are presented in figure 1. Review the procedure in part A for the preparation of a normal salt and answer the questions that follow. part A procedure. So 1, place 5 grams of sodium hydroxide solution in the volumetric flask and add distilled water to make 250 cm³ of solution. So this is our 250 volumetric flask. We're putting 5 grams. So we would have weighed 5 grams of NaOH, 5 grams. We're putting 5 grams there, and then we're adding distilled water to make up to the mark after we've done that. So we'd have 5 grams of NaOH here in 250 cm³ of water. All right, then from this, so we'd pour, after we invert this a few times, we'd pour in a beaker, then we pipette from a beaker and transfer this to a conical flask. So pipette 25 cm³ of the sodium hydroxide solution and transfer the solution to a conical flask. Then add 2 drops of methyl orange indicator to the sodium hydroxide solution in the conical flask. Part 4, step 4, place the sulfuric acid in the burette, pour it carefully, and titrate the sodium hydroxide solution until the endpoint is reached. Number 5, step 5, repeat steps 2 to 4 until consistent results are obtained. And consistent results are normally tighter volumes, consecutive tighter volumes that do not differ by more than 0.1 cm³. I believe CXC will accept the values if they're not consecutive, but really, we really want values that don't, we want values that are consecutive. That's how we do it when we're doing analytical work. Okay, so let us see what the other part of this question is asking us now. So that's the procedure for part A. All right, so this is figure 1 showing the burette readings. Now in part 1 of B, we're being asked to complete table 1, which will show in a little while by using the readings shown in figure 1. All right, so table 1 is showing titration of sodium hydroxide solution with sulfuric acid. So we're just going to record the readings that are here, then we're going to fill them in our table and do the calculation. So the first one, we have for titration 1, we have the final reading. So we will we have the final reading. So the final reading, we're just going to write this. Let's do something colorful. So the bottom of the meniscus here is sitting exactly, well, before we even read, we always have to figure out what the graduation on this the scale is. Each of these little marks, they represent, each represents 0.1 cm³. So we're going up by 0.1, 0.1, 0.2, 0.3, 0.4, 0.5. This one is 0.5. And then here, this one, the final for the rough titration is 25.5. So the initial is 0.5, the final is 25.5. So we're making a note of those. For the titration 2, the initial is 12.2, and the final is, this looks like 37.3. Titration 3, the initial is 15.5 and the final is 40.5. So we're just going to make note of those and we're going to write them in our tables, do our calculation. So let's just pull up the table. Okay, so let us just fill out our readings. So final reading titration 1, we said it's 25.1, initial 0.5. So the volume used would be the final reading minus the initial reading. So that would give us 25.0. Titration 2, this was 37.3, 12.2. The difference between those two is 25.1. Titration 3, 40.5, and initial 15.5. The difference there would be 25.0. Now, for part 2, we're to indicate using asterisk the titration volumes that will be used to calculate the average volume of sulfuric acid, right? Right, so let us do that. So here if you work with the 25, they'll accept it. However, we normally, for analytical work, we want consecutive readings that don't differ by more than 0.1. So since the first one was considered the rough one, it doesn't necessarily mean we can't use it. But in this case, in the case here, we have titration 2 and 3 that don't differ by more than 0.1. So we could just average those two. However, as I said earlier, if you decide to average 25 and 25, they will give you the mark at CXC. All right. So in the next part, we would actually show the calculation, and of course, if we're going to show it, we have to do it properly. So it would be 25.1 plus 25.0.0. All of that divided by 2. All of that is in bracket divided by 2, and that would give us 25.05 cm cube. So that would give us a mark. We don't want to lose our mark, so we are careful to ensure that we put the bracket to say to say we're adding the volumes, then we're dividing by 2. We have to bear in mind the order of operations here. So in part 4, we're being asked to complete the procedure for part B by stating the steps required to obtain a dry sample of the normal salt. So they've given us 2 steps. They've given us 2 steps here. Pipette 25 cm cube of the sodium hydroxide solution and transfer the solution to a conical flask. 2, using the burette, add the volume of sulfuric acid used to neutralize the base from part A to the sodium hydroxide solution in the conical flask. So the volume that we used was 25.05 cm cube. And as I said, we could have worked with the 25. So in step 3, we just want to continue and to the point where we're going to get a dry sample of the normal salt. All right, so the normal salt we're looking at here is sodium sulfate. We never mentioned it earlier on, but we're looking at sodium sulfate. So we're taking the simplest route, 2 steps left. So at the end of the titration, everything is in the conical flask. The first time around, we use a screen methyl orange to tell us when we would need to stop adding our acid to the base. Now in part B, we need not use the indicator because we already know what the volume is that will totally neutralize our base. And furthermore, if we were to add an indicator, then we would not have a pure sample of our salt. The indicator would be acting as a contaminant. So I think the question will more than likely ask us about that a little later on. So that's why we don't really use the indicator this time around. So step 3, we would need to transfer contents of conical flask to an evaporating dish on a water bath, or we could just simplify it. Right, so this will Then set this on a water bath and we will just evaporate the dryness. We could say gently evaporate, but the fact that it's on a water bath, that denotes that it's gentle. Evaporate to dryness. So that will give us full marks, and that's 2 marks. 2 more marks to our tally. Part 5 of B. Write a balanced equation including state symbols for the formation of the normal salt from sulfuric acid and sodium hydroxide. So here we go. Sodium hydroxide, that's an alkali, so that's aqueous. Sulfuric acid, H2SO4, and this will give us the normal salt is Na2SO4. All sodium salts are soluble, so that would be aqueous, and that's water, which is a liquid here. Now our sodium should be jumping out at us. We have 2 on the right side, 1 on the left, so we put a 2 right here to fix that. When we do that, everything that comes after the 2 for sodium hydroxide is times 2. So we'd have 2 O there and we'd have 2H. So that means the total number of hydrogens on the left-hand side is now 4. 2 from the NaOH and the 2 from the sulfuric acid. So to fix this, we would need to put a 2 in front of the water. So we now have a total of 4 hydrogens on the right and a total of 4 on the left. The sulfate is still intact, so we need not adjust that. We need not trouble that. That's fine. So everything is balanced right here. Now in part 6, we're to calculate the number of moles of sulfuric acid used to neutralize the sodium hydroxide. Now earlier on, we were told that we were given 4.9 grams per dm cube of sulfuric acid. Now that's the mass concentration. We know that from our calculations earlier, we used 25.05 cm cube of this very same sulfuric acid solution. So first things first, we know that the mass concentration we were given is 4.9 grams per dm cube. So what we're going to do first, we're going to convert that to moles per dm cube. So we could say molar concentration here, big M, is equal to the mass concentration that we're given, 4.9 grams per dm cube, and we're dividing that by, we're moving from mass to moles, so we'd have to divide by the molar mass, which is 98 grams per mole. Of course, grams will cancel out grams and we'll be left with moles per dm cube. So this would give us 0.05 moles per dm cube of our sulfuric acid. Now, this is the molar concentration. In other words, we're saying that 1000 cm cube of this solution contains 0.05 moles. So if we use 25.05 cm cube, we want to find out how many moles in that. Now, we could just tell them that the number of moles of the sulfuric acid used, H2SO4, would be equal to, we take the concentration, 0.05 moles per dm cube, and we could now multiply this by the volume that was used, but the volume that we use must be expressed in dm cube here. So to convert the 25.05 cm cube to dm cube, we divide by 1000. So we could just say this is multiplied by 25 cm cube, but we're going to convert it to dm cube by dividing by 1000. And we could have just done that before and just say, hey, this is 0.05 times 0.02505. But whenever we do that, our answer will be 0.00125 moles, or we could have written it in standard form as 1.25 times 10 to the minus 3 moles. All right. So some folks prefer to write out the statements. That's fine. That works as well. We could have here said, okay, since this is the molar concentration, we could have said 1,000 cm cube of the sulfuric acid contain 0.05 moles, and we sampled 25.05 cm cube of the same solution. So how many moles will we have present? Of course, we cross multiply, so that would give us 1,000 cm cube times x is equal to 25.05 cm cube times 0.05 moles. Of course, we'd need to divide both sides by 1,000 cm cube to make x the subject. We divide the left side by 1,000 cm cube, we do the same thing to the right side, because anything we do to one side, we have to do it to the other side. This cancels out, and we're left with the same thing we have over here. Very same thing, right? We end up with 25.05 cm cube being divided by 1,000. Cm cube cancels out cm cube. We're left with moles, and we end up with the very same thing. Just another way to approach it. And then the final thing now, final part. All right, so we're at part 7 of B. Calculate the mass of the normal salt expected from the reaction. Now, just to recap, from the question above, from part 5, we wrote the balanced equation for sodium hydroxide reacting with sulfuric acid. No, in part 6, we calculated the number of moles of sulfuric acid that reacted from the volume that we used, and we said it was 0.00125 moles of sulfuric acid. All right, so this is the number of moles of H2SO4 that we have, sulfuric acid. Now, we are concerned here with the mass of the normal salt that's expected. Now, our sulfuric acid is in this case, so our sulfuric acid is our standard solution. We knew its concentration from the get-go, and we determined that we have a set amount of it, a set number of moles of it from the 25.05 cm cube volume that was used. So if we have 0.00125 moles of sulfuric acid, we can use the mole ratio of how the acid react to form the salt to actually determine the number of moles of the salt that we'll actually get. So should have probably stated this first. If we look right here, we're seeing that nothing is there. One is there, but we don't normally say the one when the coefficient is 1. When we're talking in math, when we say we have x, when we have x, the coefficient is normally 1. So in like manner, we have a 1 right here. So we have a 1-to-1 ratio of the sulfuric acid and the salt, the normal salt. So if we have 0.00125 moles of sulfuric acid, we will get the same 0.00125 moles of the sodium sulfate being formed. So what we need to do now, they ask us to calculate the mass of the normal salt. We know the number of moles of the normal salt. So we would now need to just convert that to convert the number of moles that we have to to mass or to grams, and we would do that by just multiplying by the molar mass. Now we'd get some marks here for calculating the molar mass of the sodium sulfate. We did not show how we did it for sulfuric acid earlier, but we should show our working. So here for the Na2SO4, it would be 23 times 2, which is 46. 32 for the sulfur, they gave us the RAM, so we work with those. So that's 32 times 1, that will give us 32. And then we have 16 for the oxygen times 4, which is 64. And there we have it. This would be 4 plus 2, 6 plus 6, 12. We carry 1. 6 plus 3, 9, plus 4, 13, plus 1, 14. So the RFM is 142, but the molar mass is 142 grams per mole. So the mass of the the mass of the sodium sulfate, the normal salt, the mass of the normal salt that would be formed would be equal to the number of moles, 0.00125. For those who want to call it 1.25 times 10 to the minus 3 number of moles, that's fine. And we're multiplying by the molar mass, which is 142 grams per mole. When we punch that in, that should give us 0.18 grams. And then for the final mark to top of that 25, part 8, the actual mass of salt obtained by the student was 0.09 grams. Wow, that's half the amount that we expect, half the mass that we expect. Percent yield suggests one possible reason for the difference in the expected mass of the salt and the mass obtained. So we expected 0.18 grams, but obtained 0.09 grams. Now this could be due to a few things. We just want one of them. So it could be due to impurities in the reagent. That's REAGENTS. Or it could be due to loss of mass during transfer. And it could also be due to incomplete crystallization, depending on the approach you took to actually getting the crystals in the latter part. So any of those three would give us the full marks there. And just like that, we'd have 25 marks. Now, number 2, this looks like redox. One of the main active ingredients in chlorine bleach is the oxidizing agent, sodium hypochlorite. That's NaClO, also called sodium chlorate 1. All right, by adding sodium hypochlorite to water, hypochlorous acid, HOCl, is formed according to the equation below. And the equation is there. Now state one use of bleach in the laundering of clothes. We cannot put back. Bleach is used to launder clothes. No, we cannot do that. So we could state, I don't want to call it the obvious, bleach is used to remove stains. Another thing that we actually use bleach to do, to brighten. We could say we use it to brighten colors, or we use it to white, make your whites whiter. That's almost the same as saying remove stain, but there are some bleach products that are added to the wash to actually give the colors a boost, especially oxygen based one. But anyway, these are examples of bleach, and chlorine bleach is not the chlorine based bleach is not the only one. So your answer would be accepted. We also use bleach to disinfect in laundering. All right, so any of those would give us the marks. And then here, part 1 of B, they're asking us to define each of the following terms. So the first one, an oxidizing agent. So we could say it's the substance that accepts electrons in a redox reaction. All right, so it's a substance that accepts electrons in a redox reaction, or we could say it's a substance that is itself reduced in a redox reaction. It's a little counterintuitive, but with practice we can get the nuances. So the oxidizing agent, you're defined based on what you do. So if you're an oxidizing agent, you're called that because you cause oxidation in something else. And to cause oxidation, or for oxidation to happen, it means that you're actually pulling electrons from that other species that is becoming oxidized. So you know, because you do that, or your being there causes that, then you are the oxidizing agent. It's a little counterintuitive, but it's not impossible. All right, so let's continue to rack up these marks. Define oxidation. All right, so this one, we can think of oil or oil rig in terms of electrons. So oxidation is loss of electrons. We could have also said oxidation is an increase in the oxidation state. And for part C, we're supposed to determine the oxidation number of chlorine in the formula NaClO. Now, if we practice calling these, well, let's leave it alone. Earlier we said it's sodium chlorate 1. We look at why it's sodium chlorate 1. So we're going to use what we know to find what we don't know. So here, this substance does not have any charge. So it means that the sum of all the oxidation numbers that are present should give us 0. So sodium, it's in a compound, so it's +1. Over chlorine, we don't know the oxidation number, so we'll call that X. Oxygen here is in a compound and it's not a peroxide, so the oxidation number is -2. So we have to know the rules for assigning oxidation number. So we can take this now to write an algebraic expression. So +1 from the sodium plus X, which we don't know, plus -2, all of that is equal to 0. We can rewrite this +1 plus X plus -2 is the same as saying -2, that is equal to 0. All right, so let's group the terms that are group-like term. When we group the like terms, we're going to end up with X, and +1 minus 2 will give us -1. So X minus 1 is equal to 0. X minus 1 is equal to 0, then it means that X is equal to +1. So just add, pretty much here we're adding +1 to both sides to make X the subject. So X is equal to +1. And we got a whopping 3 marks for that. So don't take your rules for assigning oxidation number, do not take them light. All right, so 3 more marks to our tally. All right, so part D. Chlorine gas also reacts with water to form hypochlorous acid, HOCl, as shown in the equation below, and in which the chlorine has become a chloride ion. So what we're gonna do is now, let's see. All right. So what is the change in oxidation number of chlorine for the process? All right. So let's see what's happening here. So let's assign our oxidation numbers. So chlorine here in its elemental state is 0. Our hydrogen in water here is +1. The oxygen is -2. Now here we have H plus, so that's +1. The charge on this species is the same as its oxidation number, except you write the sign first for the oxidation number, but the number first for the charge. So here for the chloride, it's -1. Now in HOCl, let us see what we have. The H is plus 1. The oxygen is negative 2. And if the oxygen is negative 2, as we know, it is in a compound that's not peroxide, and it means that the chlorine here is actually plus 1. Okay, so the change in oxidation number of chlorine for the process, let us see. We have a change of, let's say, from 0 to negative 1 in Cl minus. So of course in Cl2 it's 0, and then we have another change where it is actually from 0 to plus 1 in HOCl, or in going to HOCl. Which process occurred when the chlorine gas became a chlorine ion? What's wrong with that statement? All right, so first things first, chlorine is an element. Chlorine would not say chlorine ion, so this should have been when chlorine gas became a chloride, CHLORIDE. So the last part of the name should change to give us ide. Took off the last part and we add the ide. So this should be the chloride ion. So the process for it to move from 0 to negative 1, so from 0 in Cl2 to negative 1 in the chloride ion, that process is reduction. So the oxidation state decreased, so that's reduction. And then here we want a simple test for the chlorine gas. Now, if we're given a simple test, it means we have to tell them what it is that we expect to observe. So we have to tell them what our test reagent is and what it is that we expect. All right, so to test for chlorine, we would use, so we test with this gas with damp blue litmus. And the presence of chlorine, we tell them chlorine changes it to red, then bleaches it. All right, so chlorine is acidic, but will also decolorize the litmus paper, will bleach it. So it turns the blue litmus paper to red, then it bleaches it. Okay, part E of number 2. A more natural alternative to chlorine bleach is the use of detergents which release hydrogen peroxide in water. The bleaching action of hydrogen peroxide is also a redox reaction and is represented by the following equation. 2 moles of hydrogen peroxide equals, breaks down to give us 2 moles of water and 1 mole of oxygen gas. Now, during one stage of the reaction, hydrogen peroxide is converted to water. Show the changes in the oxidation number of oxygen in hydrogen peroxide and water, and deduce whether this is an oxidation or reduction reaction. All right, so let us assign our oxidation numbers, and then we can take it from that. So let's assign oxidation numbers. So this is hydrogen peroxide. So this is +1, the hydrogen still. The oxygen here is -1. Over here for the water, the hydrogen is still +1. It's 2 of them. The oxygen is -2. Right? Over here for the well, we're not concerned about the oxidation state of elemental oxygen. They did not ask us. This would probably blow your mind. So let's just focus on what they've asked us. All right. So deduce. So let's see. Deduce. Show the changes in the oxidation number of oxygen in hydrogen peroxide and water, and deduce whether this is an oxidation or reduction reaction. So in peroxide, the oxidation number of oxygen was -1, and in water it is -2. So if the oxidation number moved from -1 to -2, it means that there was a decrease. So the oxidation number, let's write. So the oxidation number of O in H2O2 decreased, yes, from -1 to -2 in water. And a decrease in the oxidation state or the oxidation number is reduction. So this is reduction. All right, so full marks. So we can't leave out the rules for assigning oxidation numbers. Very, very important. And just like that, 15 more marks. So 25 plus 15. So far, we've tallied 40. How is it going for you? All right. Leave your comments in the chat. What have you gotten so far? How did you find this question? How was this for you? Leave a response in the comments below. Let us know how you find this. Let us know how you find this. And we're on to number 3. It's not CXC chemistry. It's not CSEC chemistry if there's no organic chemistry. You can rest assured that we will have a third of the paper, a third of paper 2 being organic chemistry. 2 full questions. So part A of 3, cracking is a very important process in the petroleum industry. What is meant by the term cracking? Put them in the dashboard, crack them up, crack, crack, crack. It's a song that some students presented when they were looking at this a while back. So cracking is the breaking down. Is fast. It's the breaking down of long hydrocarbons or long chain hydrocarbons into shorter ones. All right, I normally say shorter, more useful ones, but that tends to be over answering the question, especially since this is normally followed by why is cracking important. All right, so the useful ones are, the shorter ones are more useful. Okay, so compound A, C4H8, this is part B, and compound B, C4H10, are both hydrocarbons that can be obtained from cracking. State the name of compound A and compound B. C4H8, twice the number of hydrogens as carbons, so that is an alkene, 4 carbons long. So 1, 2, 3, 4, that would be butene. C4H10, that's from the alkane series, so that would be butane. Okay, so here we're supposed to draw the fully displayed structure of compound A, and we said compound A is butene, so we have four carbons present. Now we can put our carbon-carbon double bond between any of these. So I'll just put it between the first and the second one. Our carbons must be taking part in 4 bonds. So we ensure that we don't include them in 5 and we dress them up. We ensure that they all have their hydrogen, the correct number of hydrogen. So this would be the fully displayed structure of compound A, C4H8. We could have drawn it with the carbon-carbon double bond at carbon number 2. All right, so that's another alternative. All right, part 3. State the homologous series to which compound B belongs. So compound B, C4H10, mentioned it earlier, that belongs to the alkanes. briefly describe one test that could be used to distinguish between compound A and compound B. Write the expected results. So, okay, so we could subject both of them to bromine water. So we could subject both of them to bromine water. That's aqueous bromine, or we could use liquid bromine in tetrachloromethane, and that would give us aqueous bromine one at a time. Aqueous bromine would be decolorized. Well, actually, not just decolorized. A is the alkene, so compound A would decolorize bromine water. Let's change it from yellow to colorless. If we use bromine in tetrachloromethane, it would change it from red-brown to colorless. It would decolorize it as well. We could have also subjected both of them to acidified potassium manganate 7, and the alkene would actually decolorize the acidified potassium manganate 7. In all the cases we just mentioned, we would not get any color change with compound B, seeing that compound B is an alkene. So that's how we differentiate between our alkenes and our alkanes. We don't need to write all of them mentioned. 3, we just write in 1. So full marks again. Part C. Compound B, C4H10, can exist as structural isomers. Define the term structural isomers. All right. We could say structural isomers are organic compounds that have the same molecular formula but different structural formula or different arrangement of their atoms in space. So we could say, well, we're not going to just say we could say it, we're going to say that. All right, that's it. Part 2, in the space provided below, draw fully displayed structures of 2 isomers of compound B. No, they did not ask us to draw compound B earlier, so we should not have an issue to find 2 isomers. In fact, it's 4 carbons long, so we would only have 2 isomers. So let's just look at that. So this is the normal one, N-butane, normal, N for normal. That's just the regular straight chain, no branching. And then we are to now rearrange this so we get a different arrangement. If we bend it, it's still the same thing. So the only way to actually get a new arrangement is if we actually cut off the methyl group right there. And we could now take this and switch places with one of the hydrogens from the middle carbon now. So we're cutting this, cut, and the methyl group will be hanging. So we'll now trade places with either the hydrogen at the top here or the hydrogen at the bottom. And that would give us our isomers. So Our longest chain in this isomer or in this organic compound would now be 3 carbons. So we're putting the methyl group here. So we're putting it on first. So we see what's happening. So this very group is what we're talking about. Taking it and we're putting it on carbon, which is, well, carbon 2 now. So this would be, we'll just put on our hydrogens to ensure that we have the same molecular formula, the same number of hydrogens, which is all of 10. So we have the same molecular formula, but just different arrangement of the atoms in space. So it's still C4H10, still C4H10. And there we go again, 2 more marks. So of course, we don't need to do the scissors. The scissors is just for illustration. Okay, part D. Last question for number 3, or last part. Compound A, the alkene, I think that was butene, burns in oxygen with a sooty flame. Write a balanced chemical equation for the complete combustion of compound A in excess oxygen. Now they said excess oxygen, well, and there's a complete combustion. So we know that we're going to get we're going to get carbon dioxide from this process. So it's C4H8 via liquid. Could get it as a gas. In fact, first four fractions. So this plus O2 gas. This will give us, once it's combustion, we're getting carbon dioxide and we're getting water vapor. We always balance in the order. Sure. Not out of frustration, we're just balancing that order. So we start off, 4 carbons are on the left hand side. We have 1 on the right. Let's just put in what we have first to begin. So 4 on the left, we have 1 on the right. Hydrogens on the left, 8. Hydrogens on the right, 2. Oxygen on the left, 2. So far on the right, we have 3. Now we start in the order choke. So we need a 4 in front of the CO2, and that should fix our carbon. But in doing so, whatever comes after this, whatever comes after the 4 in the carbon dioxide is multiplied by 4. So we've just added pretty much 2 oxygen there, because it was CO2 before. No, we've added more than 2. We've added 6, because it's now 8. It was 2 from the CO2. Now it's a total of 8 from the CO2. So that's plus 6 oxygen. Now we leave the oxygen for last. So we now look at the H. 8 is on the left hand side. We have 2 on the right hand side. So if we put a 4 here, that will fix that for the hydrogen, at least for now. Let us see. So 4 2 is 8. We now have this times 4. So we have a total of 8 so far. Putting a 4 right there means that we now have an additional 3 hydrogens. So total hydrogens on the right so far, let's check. 4 2 is 8, and then we have 4 1's 4, so that's a total of 12 so far. Hydrogen so far, 2 4's, 8. Carbon so far, 4. Now on the left hand side, we still have 4 carbons, so those are fine. We have 8 hydrogens on the left, that's fine. So it's now just the oxygen that is off. And we have a total of, as we said earlier, on the right hand side, we have 12. So this shouldn't be hard to balance. We have 2 on the left side, we have 12 on the right side. Are we seeing that 12? Let's fix that 12. Okay, so we would just need a 6 right here. That would fix it. Everybody, check. And just like that, full marks again. So we're at number 4. Graphite and diamond are two allotropes of carbon. Define the term allotrope, not allotropy or allotropes. Define the term allotrope. So this would be, so it's each of two or more different physical forms that an element can exist in. Part 2 of A for number 4. Draw the lattice structures for diamond and graphite. All right, so for diamond, we can just do it simply. I'll just do the little that I learned not a few, but some years ago. So we have one carbon bonded to, to 4 others. So we can leave it there. If you wish to go on, you could go on. But you don't really want to overdo it. You just want to show that each carbon atom is bonded to 4 more. So this, we could just leave it as that, or we could have used the first 4 that were drawn. So this is a repeating thing in 3D. We're not going too crazy with the 3 dimension. So we could have gotten the marks for just stating, for just drawing this portion. All right, so that's fine. These are very right, and these we can just say that these are strong covalent bonds. Strong covalent bonds. Now, for the structure of graphite, it requires a little bit more. We get hexagonal rings of carbon atoms. So we have each carbon atom bonded to 3 others. And we get layers. Now, if you don't stop yourself, you'll go on and on with this. So I'll just do one more. Don't need so many. So that's one layer. I'm going to do another layer here. And the key is to just practice. Take that back. So in between the layers, we have weak intermolecular forces of attraction holding them together. Right? So that's that. So these would be weak intermolecular forces, or we could call them van der Waal forces. And these are our hexagonal rings of carbon. That would give us our marks. All right, B of 4. Like metals, graphite can conduct electricity, but diamond cannot. Explain in terms of bonding why graphite conducts electricity, but diamond does not. So this stems from what we looked at earlier. You can always replay or rewind it and always touch it back. In our graphite, we have each carbon atom is bonded to three others. And we know carbon to begin with is tetravalent. That's 4 electrons in its valence valency shell. So if each carbon is bonded to 4 others, it means that for every carbon atom, there is an electron that is not involved in bonding. So if we were to apply a voltage, then we would actually have something to carry the current in graphite. Unlike in diamond, where we have each carbon atom is bonded to 4 more. So all the electrons are involved in bonding in diamond. So we could state that all right. And every time I say it, I think I say it a different way. The same should apply for you. So in diamond, all electrons are involved in bonding as each carbon atom is bonded to 4 others. In graphite, there is an electron free to carry a current for every carbon atom if a voltage is applied. And the diagram above should substantiate this. We don't have to say everything from scratch, seeing that we drew the diagram correctly above. Part 2 here, describe the bonding present in metals. Don't need to say much that in metals we have cations, metal ions, positive ions that are embedded in what we call a sea of delocalized or what we call mobile electrons. It will be a little redundant by saying positive metal ions. We're just describing it. That should do it. All right, part C, sodium chloride is a solid at room temperature. Sketch the lattice structure for sodium chloride. Okay, so we just need to be able to draw 3D somewhat. It doesn't have to be perfect. Our ability to do an isometric projection is not being tested here. This should do it. Anything more than this makes it a little untidy. And though I've said that, I'm still going along. So we'll go. We're seeing the front side, the top side, the bottom side, the sides at the back. So we're not going to shade, no shading. So we're going to put in a fluoride here, and then the smaller sodium in the middle. Fluoride at the end, sodium in the middle. Fluoride at the end, sodium in the middle. Fluoride at the end. You could have put your sodium at the end, as long as we show that they're alternating. Sodium in the middle, fluoride on top, fluoride, 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 fluoride at the corner, or that vertex at the back going into the page. So we continue. Sodium, sodium, All right, so let's make it interesting now. So this is connected to that, this is connected to that. Sodium, so we take this line down. Same thing happens at the top. Okay, at the front we need sodium, sodium. So we need a big chloride here. Easier to do on paper. And we can pretty much leave this here. It gets a little confusing. We could have stopped a minute ago. We'll show them that this is the chloride ion. And this is the Na plus ion. That would give us the mark. And the bonding, part two, the bonding, the type of bonding that exists in sodium chloride would be ionic. For again, 15 more marks. All right, so 5A, number 5, part 1 of A. Ethene undergoes a halogenation reaction to form 1,2-dibromoethane. Draw the fully displayed structure of ethene. Whoa. Right, we give thanks for small mercies. And the molecular formula for 1,2-dibromoethane, molecular formula that would be.
So for us to get 1,2-dibromoethane, it means we would have to add bromine or two atoms of bromine across the carbon-carbon double bond, and we would end up with a saturated compound. So as is, ethene is unsaturated. It doesn't have the maximum number of hydrogen that it can have. So adding the bromine across it makes it saturated.
All right, 3, draw the fully displayed structure of 1,2-dibromoethane. So after we've added those two bromine atoms, we should now have a saturated compound. I mean, we really don't put them beside each other when we'll go further into chemistry, but it's accepted at this point as long as we have a bromine on each of those carbon atoms, then we're fine. And we're stating in part 4 whether the halogenation of ethene is an addition or a substitution reaction. Now it's an addition reaction. That should give us the marks. We're at part B of number 5, organic chemistry section, and we're just going to take our time. Dibromomethane, keyword, thing here, di means two, bromo, bromine, and then methane. Dibromomethane can be obtained from methane. This reaction takes place in 2 steps. Write balanced chemical equations to show each step in the formation of dibromomethane. Right, so first, here we would need methane to start with. It's a gas. We're going to need bromine. Bromine here would be a gas. We would need UV light or some form of electrical discharge to actually split the bromine. And then when we split the bromine, we're going to get 2 bromine radicals. We call the radicals hotted. They're very, very reactive. All right, so each of them would actually take one of them would actually take the place of a hydrogen. And it's really, to not really preempt the question too much, it's a substitution. This is an alkane. So our bromine is going to take off one hydrogen one at a time. So perhaps it's best if we show the bromine in red. Okay. So if we take off one hydrogen at a time, then it means that the first thing we get is going to be, so that's Br. This should be a gas. And then we would also get, okay, something's missing there. All right, let's state it again. So we'll get C, CH3, and we'll have a Br. This should be a gas. Now, one of the other bromine, it's not forgotten. It's 2 started out with, that has gone to give hydrogen bromine. So in the presence of more bromine, we can take the product that we got here, bromomethane, or monobromomethane to be a little redundant. This would now be the starting material in the next, in step 2. So that's CH2R, which is a gas. And we're going to subject this to more bromine. Again, UV light, and this time we're going to take off another hydrogen. So we now have 2 remaining. So it's CH2, and we now have Br2. By this is the liquid, and again we would have H, Br. Yes. State whether the halogenation of methane is an addition or substitution reaction. Now, alkanes are not as reactive as our alkenes. So this is a substitution reaction, free radical substitution. Get familiar with that term, right? So that is that for that section. I think CSEC got a little soft because this time around, ethene and propene are typical monomers which are used as starting materials for making polymers. It's almost like this is a follow to what was in part 3 where they spoke about cracking. So these are some of the smaller, more useful compounds that we get when we crack a long chain hydrocarbon. So they are used as precursors or what we call starting materials for making polymers. Now, in forming polymers, ethene and propene undergo addition polymerization. Now, they're asking us they're asking us to define polymer. So this is a it's a long chain molecule formed from the joining of many monomer, monomer, monomer units. And we're to define the term addition polymerization. So it's the Okay, so define the term addition polymerization. We can call this the joining of many alkene monomer units to give a long chain with no byproducts. So at the end of addition polymerization, we only get one straight chain. We don't get the elimination of any small molecule. Now be sure to check out addition polymerization or addition versus polymerization by checking the links below or the links below this video. All right. If you've missed that showdown or that series, please check the links below. Then we're being asked here to state one use of each of the following polymers. State one use of each of the following polymers. I believe CSEC got a little soft because here, so polyvinyl chloride, we use these to make electrical conduits, or pipes. We call it pipe electrical conduits. All right, so it's used in the manufacturing. So of course we could say it's used to make electrical conduits. And I learned recently that it's also used to make plumber's tape. Used to make plumber's tape or what they call threading tape. Threading tape. All right. Teflon now, as I said, TXC has gotten soft, very soft. Soft with a capital T, like this T that starts Teflon. So Teflon, I always say in my other sessions that Teflon is not that tough. Who or what is Teflon? Teflon is not that tough. Perhaps Kevlar would have been a cooler name or a tougher name. But Teflon, we used to make the non-stick material in frying pans and pots, or in pots, those stylish pots, right? So that's made of Teflon, polytetrafluoroethylene, but I guess that's not really a good, it doesn't flow off the tongue readily where marketing is concerned. So Teflon actually would just sell better. All right, so that will give us 15 marks for that section. How have you fared so far? Let us know in the comment. And remember to just take a moment to hit that button with a thumbs up and just share with a friend if you're finding value here. Okay, so we have one more question to go. Okay, so we're at number 6. The most abundant gas in the air by volume is nitrogen. What percentage of the air is nitrogen? Okay, I'm just asking that. Put it in the comments. Stay sharp. List one physical property and one chemical property of nitrogen. All right. One physical property, one chemical property. So what do we know about nitrogen? N2. Now we know it has a triple bond, and that makes it very, very stable. But as it relates to physical property, we could say it's a gas at room temperature and pressure. It's a gas at room temperature and pressure. A gas at RTP. We could say it's colorless. Odorless. These are properties we learned probably in grade 4 about water. Water is colorless, odorless, tasteless. But anyway, this is about nitrogen. Okay. Another thing about it, physically, it's insoluble in water. So any of these would give you the mark. And it is slightly less dense than air. Not going to write all of them. For the chemical properties, now we're talking about how these behave when they undergo a chemical change, when they react. So we could say the nitrogen reacts with oxygen to form oxides. that would work. It would, we also could say it react with metals to form metal nitrides. All right. And now part B is asking us to, let's see, when gases are produced in a school laboratory, there are three main methods in which they can be collected, or three main ways in which they can be collected: upward delivery, downward delivery, and displacement of water. Upward delivery is going up. Downward delivery, it's being delivered in a downward manner. And the displacement of water. Now list two factors that should be considered when choosing an appropriate method for the collection of gases in the lab. Now, since we can collect it by the displacement of water, well, the first thing that comes to mind, or not necessarily the first thing, we need to think about its solubility in water. If it's soluble in water, it's not going to displace the water. It's going to do another D word. It's going to dissolve in the water. We also need to think about the density of the gas. All right, so we have to think about the density of the gas in relation, I would say, with respect to the density of air, density of the gas with respect to air, or relative to the density of air. So if it's a gas that is more dense than air, we're not going to use upward delivery because that gas is going to fall. And we also need to think about the reactivity of the gas with the drying agent that we're using. We could say the pH of the gas. If we're going to be making a gas that is let's say acidic, we could not use something that's basic to actually dry it. We couldn't use a basic drying agent. So I have to bear that in mind. Any two of those would give us the marks. Okay, part 2. State which one of the three methods is best suited for the collection of ammonia gas in the lab. Now, let's look at ammonia. Now we have the upward delivery, the downward delivery, and we have the displacement of water. Now, which one of the three methods here is best suited? First we have to kind of know something about ammonia. We have to know about its density. We have to know if it's basic or if it's acidic. We have to know what else? What's the other one? Density is covered in the upward or downward delivery. We also have to know about its solubility in water. Because if it's soluble in water, we're not going to collect it over water. It's not going to displace water. One, it's soluble in water. It dissolves in water to give us aqueous ammonia or ammonium hydroxide. So we're not going to collect it using the displacement of water method. It's less dense than air, so we're not going to use the downward delivery. So with that in mind, we're going to actually use the upward delivery. So one, we're going to state what we're going to use. We're going to use the upward delivery method. So the upward delivery method would be used, and the reason is because NH3 is lighter or less dense than air. All right, so we're going to say why the other two would not work. No, downward delivery would not work based on what we just said. So downward delivery is out, all right, not so formal, as NH3 is less dense than air. The other thing that we need to state, displacement of water is out as well. And we just keep the language simple. Out as well, since ammonia is soluble in water. That should give us our 5 marks. All right, so here we are asked to draw a label diagram of the apparatus which could be used for the preparation of dry ammonia in the lab. Ensure that you identify on your diagram the location of the reagents to be used and the drying and collection areas of the ammonia. All right, so we'll need our reaction flask over this side. We're going to apply heat here. What's going to be in it? We're going to need a base plus an ammonium salt. Okay, so calcium hydroxide could be used, CaOH, well, bracket OH, bracket 2, could use ammonium chloride as well. Yeah, and then here we're going to have a YouTube. This is not only set up, not YouTube, but you'll see why we call it YouTube. It's actually shaped like a U. All right, so this is packed with calcium oxide, and that's our drying agent. This is the U tube, literally. So the CaO is the drying agent. And then from here now, we're going to, since this is lighter than air, we're going to have the upward delivery. Actually found this terminology a little, not confusing, but there was a term that we used when I was in high school. We said the upward delivery, but while it is the upward delivery, it actually displaces, well, we call it, it's the upward delivery, but as the gas goes up, it displaces the air down. So we call it could be referred to as the downward displacement of air. But we'll just stick to one, the upward delivery. And that's that you could put a piece of red litmus here. So we test to ensure that this is actually ammonia, seeing that it's the only alkaline gas. So this is an inverted, this could be an inverted gas jar that we use here, right? And that's our delivery tube. And this should be, we would not use concentrated sulfuric acid. That's the drying agent. That's an acid. Ammonia is basic. So we want to have our actual product at the end. So this would be fine. This should give us our full marks. All right, so this part is the last bit for our remaining 2 marks. Okay, so we're almost there. Just hang on. Okay, ammonia is mainly used in fertilizers such as ammonium nitrate. Ammonium nitrate. Well, I guess we could say this is doubly soluble. NH4, NO3. All nitrates are soluble, all ammonium salts are soluble. Explain how nitrate fertilizers can be harmful to the environment. So, well, all nitrates are soluble. So one, when we use these fertilizers, they leach through the soils, they dissolve, they eventually reach the waterways. Now, when they reach the rivers, whatever they reach, these bodies of water, they result in what we call rapid growth of green plants and algae. We call this eutrophication. Now, when these plants and algae die, they use up aerobic bacteria, which multiply, yes, and use up dissolved oxygen. No, while this dissolved oxygen is being used up, aquatic organisms end up starving, not having not from food, but they don't really have the oxygen, so they die. They die as a result. So we could say, how do we put this in words now? We could say the result in the overgrowth. All right. And if you're not so wordified, not a word, then you can say it in fewer words. You can say it based on how you're comfortable stating it. As long as you state that, you know, eutrophication takes place. So this is pretty much talking about eutrophication. And just like that, we've come to the end of this session. Please let us know in the comments below if you found value here. And of course, if you found value, then be sure to hit the like button, share so others can find value, and consider subscribing if you have not done so. Now, as we always say on Chem with Chem, couple later. And just like that, we've come to the end of this paper, the end of this session. I hope you found value in this. If you did, then just leave a comment about that and share with a friend. Remember to leave a like. And if you haven't subscribed, please take the time to do so. See you in the next video. Thanks for making it Chem with Chem. Peace.